Today I'd like to talk to you about scalars, vectors and all that with a very specific aim in mind, and that is to give you the proper definition of these quantities after motivating the reason for using these quantities in the first place. Now, all the physical quantities that we deal with have certain specific mathematical characteristics. For instance, they are classified as vectors, tensors, scalars and so on and so forth. Sometimes you classify them depending upon their action, such as operators of various kinds, matrices and so on. There are lots of mathematical quantities, but the most common ones that you come across in elementary physics are scalars and vectors, and we would like to understand what these quantities actually are and why we need them at all in the first place. This is crucial because all physics is based on the use of such quantities. Okay. First, you would have heard of what a scalar is and what a vector is, and let me recall the high school definition of these quantities, the naive definition of it. So the naive definition says, naive or simple minded definition says the following: a scalar has only a magnitude. On the other hand, a vector has both magnitude and direction. I am going to right away puncture these definitions by saying they are not adequate, they are not enough. For instance, suppose you look at the coordinate of a point in a plane. Now, as you all know, if you take a plane, the xy plane for instance, here is the x axis, the y axis, here is the origin, and let us look at some particular point P whose coordinates are x and y in Cartesian coordinates. What this means is that this distance here up to this point is x and this vertical distance is y. Okay. Now, this x can run all the way from minus infinity to infinity, and so can y on this infinite plane. And the question now asked is x a scalar? Well, you would say x has a sign, it has got both plus and minus possibilities. So why not this? Why not this quantity? Is this a scalar? Because it has only a magnitude, and that magnitude runs anywhere from 0 arbitrarily high to arbitrarily high values. So the question is it a scalar? And the answer is no, it is not a scalar. Similarly, when you say you have a vector as a quantity with magnitude and direction, the immediate question that arises is direction with respect to what? And the answer is direction with respect to some fixed coordinate system. But there is no special coordinate system, and who gives you this coordinate system anyway? So the point is this definition is inadequate. While they are convenient, and once we know what we are talking about we could use these definitions, the fact of the matter is they are not rigorous definitions and they are highly incomplete. So we need a proper definition of these quantities as well as an explanation, as I have said earlier, of why we use these quantities at all. And here is what it looks like, the answer is. And let me do this in terms of an example. Here is the example. You are familiar with Newton's second law, which says that the force is the mass times the acceleration. For a body of mass m in Newtonian mechanics, once you apply a force, the result is an acceleration of the body, and the acceleration is proportional to the force. This is Newton's second law of motion in its simplest form. Now the question is, these directions of f and a are specified obviously with respect to some fixed coordinate system. So here is my coordinate system, and let us for the simplest case look at just two dimensions. Here is x and y, and my coordinate system, let me call it S, my fixed coordinate system here. And in this coordinate system, this quantity f has two components, an x and a y component. So let me write it this way: f subscript x, f subscript y, and this quantity a has two components, ax and ay. Okay. On the other hand, the same physical force on the same physical body with the same mass could be examined in some other frame of reference. So there could be a coordinate system for an observer S prime whose origin is sitting here, O prime, and this is y prime and this is x prime. Now the question is, what is he going to observe in this experiment on this body of applying this force. It is quite clear that since f sub x and f sub y are the components here with respect to this origin here and this frame of reference, these numbers are specific to this frame of reference. These numbers are specific to this frame of reference. On the other hand, that might lead to a totally new result altogether, and yet your textbook says f is ma without bothering to specify where the coordinate system is. So the logical conclusion is that it is probably independent of this coordinate system. In other words, in this coordinate system, the presumption is that the rule must be f prime, which is the force observed in S prime or measured in S prime, must be equal to m times a prime. We made a little assumption here which I have pushed under the rug, that m does not change and it is a scalar, so in some sense I am already begging the question, but let us take it as m as the naive definition of m, which is that it is the inertial mass, it is a property of the substance, has nothing to do with coordinate system or anything like that. Then we expect that in this frame of reference the law will be the force in this frame is the mass times the acceleration in this frame. Once that is true, then it does not matter, you do not have to specify which frame you are in, because it is true in all frames appropriate to each frame. This person's components would be f sub x prime, fy prime, and that acceleration would be ax prime, ay prime on this side. Just one thing left to do, and that is to say that since the law is the same in form between this frame and this frame of reference, it can only be expressed in terms of quantities whose transformation property is encoded in the quantities themselves. In other words, this quantity f and this quantity a, vectors, must carry a dictionary in their very meaning, which tells you that if you tell me how the coordinate system S prime is situated with respect to the coordinate system S, and you give me this rule f is ma, then I predict for you what the numbers fx prime, fy prime, ax prime and ay prime are. In other words, if you want the physical law to be unchanged in form, to be form invariant under a coordinate transformation, you must express them in terms of quantities whose transformation law is known, is prescribed once and for all, and such quantities are called covariant quantities. This is such an important principle, and it is at the root of modern physics, that I am going to write it down. Physical laws are expressed in terms of covariant quantities so that they remain form invariant. Now that is a lot of big words for something which is a very straightforward matter. It simply says that our laws, we believe, more and more generally are independent of the observer. The whole of modern physics is an effort to discover laws of nature in such a manner that they are completely independent of the observer's special status. For that, you need to express these laws in a form which does not change when you go from one observer to another, and to do that you need to express them in terms of quantities which carry their own transformation laws, their own dictionary, and scalars and vectors and generalizations are such quantities under specific kinds of transformation. So this is what I would like to emphasize, and this is what I would like to show today, demonstrate today. I repeat once again, the reason for us to use scalars, vectors and so on, in particular vectors you can write in 3 dimensions, you can write 3 equations in one line. When you write it in terms of vectors, it is not to save space, it is to make sure, it is necessary to make sure that you are expressing form invariant physical laws in a manner where you can translate from one frame to another or from one observer to another. In this case, if f and a are vectors in the definition which I am going to give shortly, then you are guaranteed that the law f equal to ma is form invariant under the transformations from one observer to another or one frame to another under which these quantities are vectors. That set of transformations will be seen shortly, and under that set of transformations you are then assured that this law will not change its form. Numerically, yes, it will change, because any acceleration you measure in this frame, the numerical values that you have for these components at any instant of time would be different from the numerical values you have in this frame, as would the force components. But what you are assured is that if you give me f and a, the components of f and a in this frame, and tell me how O prime is related to O, how far is it moved, how much is it rotated, then I will predict for you that in this frame you will discover f prime is ma prime, where the f prime quantity, the quantities which are prime, can be found from the quantities which are given in the unprimed frame here. So this is the idea behind the whole thing. Now what is the definition of a vector, what is the definition of a scalar? This is now going to be a matter of detail on what kind of transformation we are talking about, and the one that is used conventionally for vectors at this level are called rotations of the coordinate axes, and let me explain what that does. So as before, we are going to take a very simple example, which is rotations in a plane. So for the moment, let us pretend our world is two-dimensional, that we have just the blackboard as the world that we are talking about, and there is a coordinate axis here, x and y. Here is the origin, and you have an arbitrary point with coordinates x and y in the frame S, in the original frame S. So that this quantity is y and this is x for an arbitrary point x comma y. Now let us look at the same thing in a frame of reference which has the same origin but is rotated with respect to x through some with respect to the x axis. The new x axis is at an angle theta, some arbitrary angle theta. And here is the new y axis. This angle is theta. That is the x prime axis, this is the y prime axis, and this angle of course is also theta. Then how are the components x prime and y prime of this object, of this point done? So here is a point P which is either xy or x prime y prime in the new coordinate frame, and then it is a simple matter of trigonometry to see that the transformation rules are x prime is x cos theta plus y sin theta, and y prime is minus x sin theta plus y cos theta. Those are the transformation rules which follow from elementary trigonometry. And together, of course, I call the point r, the position vector of this point is written as r either in the original frame and r prime in the new frame. So r equal to x times a unit vector in the I direction plus a unit vector in the j direction. We can write it either way you like, but I am just going to write it as x comma y in this form here, and under this rotation r goes to r prime, which is x prime y prime under rotation of the coordinate axis. So each point, although the point remains the same, the coordinates change, but I could regard it as a transformation from xy to a new set of pair of variables x prime y prime. Okay. And the rules by which you get x prime and y prime from x and y are written down here in this form here. Now it immediately tells you right away that x prime squared plus y prime squared is x squared plus y squared. That is a simple matter of using the trigonometric identity, cos squared theta plus sin squared theta is 1, and then you get this relation here for an arbitrary point x comma y. Now what does that mean? the physical meaning of this x squared plus y squared is of course this length of this hypotenuse. So this distance here is r, but it is also equal to r prime, which is what this quantity is, because remember this number here was y prime and this number here was x prime. So that is x prime, that is y prime. And the square of this plus that is this squared, which is the same as the square of this plus this here by the Pythagoras theorem. So we know our first relation, which is r and r prime, are exactly the same. In other words, the distance from the origin to any point is independent of the orientation of the coordinate axis. If you rotate the coordinate axis keeping the origin unchanged, the distance to any point does not change at all. And physically it is immediately clear that the distance between any two points, arbitrary points, also does not change at all, because the distance between a point x1 y1 and x2 y2 is just x1 minus x2 squared plus y1 minus y2 squared, and that too does not change at all. So now comes the definition. If you have a quantity which does not change under rotation, I call it a scalar. If it does not change in magnitude, it does not change at all under rotation, it is then called a scalar. Okay. So r is a scalar. R equal to r prime. The prime quantity and the unprimed quantity are exactly the same. Any quantity that does not change under rotation as you go from one frame of reference to another is a scalar under rotations. I need to say that all the time because I might look at more kinds of general kinds of transformations, but for the purpose of this course we will restrict ourselves to rotations because that is what normally vectors, scalars, tensors, etc. are defined in terms of. So this quantity is a scalar. What then is a vector? Well, as you know, in the naive definition it has a magnitude and a direction, and a little more sophisticated way of saying it is it's got two components. Once you have a two-dimensional world, a vector has two components. For instance, the position vector of a point is r, x comma y. This is our primal vector. This thing here is our primitive basic vector, this quantity here. And now the definition is that any quantity with two components, so anything like let us call it u and put an arrow there, and it has got two components ux and uy, any quantity with two components written in this form which transforms under a rotation in the same way that the coordinate r itself transforms is called a vector. So this is a vector if and only if under a rotation of the coordinate axis through some arbitrary angle theta, only if u goes to u prime, which is equal to ux prime and uy prime, where ux prime must transform exactly like the corresponding component of the coordinate itself. So it must be equal to ux cos theta plus uy sin theta, and uy prime must be equal to minus ux sin theta plus uy cos theta. That is the definition of a vector in two dimensions, a vector under rotations and so on and so forth, but that is the definition. Therefore, any two arbitrary quantities, if you put them next to each other and put them inside a bracket, cannot form a vector. A vector occurs only when these two quantities are such that the pair is such that under a rotation the pair transforms in precisely the same way as the position vector itself does. So it is with reference to the transformation law of a position vector, a point in space, that we define a vector itself. Okay. Once you are guaranteed that the quantity is a vector, then we use the fact that it transforms in this fashion to predict what the prime quantities are from the unprimed quantities by a rule which is the same as the rule for coordinate transformation itself. Okay. So this is the correct definition of a vector, and it is extendable to any number of dimensions. If you have a third dimension, a third axis coming out of the paper, there would be a u, there would be a z also as well, a z prime coordinate, and it should transform in exactly the same way the x y z transforms to x prime y prime z prime. Any set of three quantities which transform in the same way as the three Cartesian components of the position vector would then be called a three-dimensional vector in 3 dimensions. So this is the notion of what a vector is, and that is how the transformation law is encoded in the word vector itself. The moment I say something is a vector, I have also told you how its transformation law is going to behave, and that is going to make sure that any law I express in terms of vectors is transformable from one frame to another without a change in form, because I know how each side of the equation transforms. They transform like vectors. Okay. Now it is a small matter to see that if you have an equation with a left scalar on the left hand side, you should obviously have a scalar on the right hand side, because neither side can change. If you have a vector on the left, you must have a vector on the right, and so on and so forth. There are generalizations of vectors and scalars which we will talk about a little later, very straightforward generalizations, but this is the basic idea behind a vector here. Now we need a little bit of notation so that we can generalize this a little more, and that is as follows. It is very convenient to notice that I could write those two equations down, x prime and y prime. I could write them down in the following convenient way. I put these two as a column vector, one below the other. This thing here is a 2 by 1 matrix. It has got 2 rows and 1 column. So it is a 2 by 1 matrix. I presume there is some familiarity on your part with elementary matrices, but whatever is needed we will look at it as we go along. We will introduce that. This quantity here is equal to x comma y. This too is a 2 by 1 matrix, and it must be acted upon, as we say, by something which is a 2 by 2 matrix, and that is the matrix of coefficients there, whatever is multiplying x prime and y prime. So that thing is cos theta sin theta minus sin theta cos theta, and by the rule of matrix multiplication, this is a 2 by 2 matrix, and as you know, when you multiply 2 by 2 by 2 by 1, the 2's cancel out, so to speak, and you get a 2 by 1 once again. So this gives you a column matrix here, a 2 by 1. This 2 by 1 column matrix, when acted upon by this matrix here, gives you a 2 by 1, the new column matrix, which represents the position vector in the new coordinate system. Okay. Now what would you call this matrix? Well, it is a matrix which depends on the angle through which you rotate. Could have been any angle. I specify the angle, I give you a new coordinate system. So it is not unnatural to say that this thing here is called a rotation matrix. And it depends only on the rotation. It does not depend on the coordinate of any particular point, because that is the whole issue. Any point, anywhere, any point here is transformed. In the old coordinates, it has got a certain components. In the new coordinate, it has got different components which are related to the old ones by the action of this rotation matrix on the old components in this fashion. This matrix is 2 by 2 because we have 2 dimensions, and what has happened under a rotation is that you have a linear transformation. So each component of the new vector is a linear combination of the components of the old vector, all the components. So the x and y components of the old vector have been mixed up to give the x component of the new vector, and similarly for the y component as well. It is a linear transformation in the sense that the origin has been unchanged. So it is clear that if you are at 0, 0, the origin in the old frame, you are still at the origin in the new frame, which means that if you set x and y equal to 0, you must get x prime and y prime equal to 0 as well, which you do because these are homogeneous transformations. A rotation, a proper rotation, is a homogeneous transformation in the sense that the origin is left unchanged under the transformation. Now the generalization of this to 3 dimensions is easy in principle. In practice it is a little messy because as soon as you have 3 components, as soon as you have a 3-dimensional space and here is x, here is y and here is z, then you need for any point you need 3 coordinates x, y, z. And now a rotation is not such a simple matter as keeping the origin unchanged and rotating the coordinate axis, because if you have a 3-dimensional space you could rotate about any direction in that space. So here is a direction in this space, original coordinate frame, and I can rotate about that axis in this fashion to produce a new set of axes here. So we have to specify the direction about which I rotate, and I have to specify the amount by which I rotate. To specify the direction in space you need 2 coordinates, you need 2 angles, just as to specify the position of a point on the surface of this earth you need a latitude and a longitude. So to specify any direction, the unit vector in any direction, you need to know 2 angles essentially, and then you have a third angle which is the angle of rotation. So you have 3 parameters to specify a rotation in 3-dimensional space, and therefore the matter is a little more intricate, but you are still guaranteed that under the rotation in 3-dimensional space you have the following. You are still guaranteed that under this rotation x prime, y prime, z prime now will be equal to some 3 by 3 rotation matrix multiplying, acting from the left on x, y and z. And this rotation matrix will not involve x, y and z themselves, because this is true for every x, y and z in space. This rotation matrix will involve the 3 angles which are the analog of the single angle here which specifies a rotation in a plane. So it is a complicated matrix, it has got very special properties, but all the same it is a rotation matrix, and you are guaranteed that in general what is going to happen is that x prime, if I call this matrix R, then this x prime is going to be R11, the first element, times x, plus R12 times y, plus R13 times z, and similarly y prime is R21 times x, 22 times y, plus R23 times z, and z prime equal to R31x plus R32y plus R33z. So each component of the new vector is a linear combination of all the components of the old vector. Some of these components may or may not exist depending on what kind of rotation we are talking about, the specifics of the rotation, but that is the general structure here in this. And you are guaranteed that this matrix is such that the analog of the property that r squared equal to r prime squared is still going to be valid. So it is still true that the distance to any point from the origin clearly does not change under a rotation which keeps the origin unchanged. So you are still guaranteed that r squared is r prime squared and that r is a scalar in this quantity. Now you can answer this question of whether in this example or in this example mod x, is it a scalar? The answer is no, because x goes to x prime and x prime is this complicated combination here. So clearly the modulus is not invariant, does not change. So x is a component of a vector and it is not a scalar by itself. That is an important point. One should not imagine that when you have a vector comprising several components like this, or in the case of u like this, one should not say this is a scalar or that is a scalar. Not true, because these quantities do not remain unchanged under a rotation. They combine with each other, they mix up components and they do not remain invariant. On the other hand, you are certainly guaranteed that u squared, the magnitude of ux prime squared plus uy prime squared, the quantity, is equal to ux squared plus uy squared, just as x prime squared plus y prime squared is x squared plus y squared. Okay. So this quantity u, this fellow, is indeed unchanged under rotations and is a scalar. Okay. But the magnitude of any one component is not a scalar by itself. So this is the idea behind scalars and vectors in the most elementary level, and what we will do next is to see how we can form scalars from vectors, and a little later we will form vectors from scalars. So that is because these are natural quantities that appear all the time, and we need to be able to manipulate these quantities and understand it. We also need to see how we can multiply two vectors. What is the geometrical meaning, actual meaning of the dot product and the cross product in the case of vectors, and there are a few minor surprises on the way. So we will see that next.